Hi, my name is Anas, and I will be talking about how we use machine learning to pinpoint special regions in a given material. Here is the big picture. A single light particle is called a photon. A material that emits singular light particles is the building block for quantum technologies. Multi-slice algorithms can simulate all possible experimental images for a given material. We can analyze thousands of experimental images using a convolution neural network. A collection of simulated images can be used as references to analyze experimental images using the neural network. Here is the motivation for my research. Consider the transistor. Based on the voltage we apply to the gate here, it raises or lowers. When the gate raises, it allows for electrons from the source to travel to the drain. The higher the voltage we apply, the more electrons can flow. The central processing unit, which is the brains of your computer, uses billions of these transistors to carry out commands you provide to it, such as opening Google Chrome or turning off the computer. Moore's law states that as transistors get smaller and smaller, the number of transistors we can fit on a CPU increase exponentially. However, the smaller the transistor gets, the thinner the gate gets that blocks the flow of electrons. If the gate is thin enough, the electrons can just magically go through the gate through a process called quantum tunneling. This is why we are capped at a certain density of transistors on a chip. If we added any more transistors, then quantum tunneling might make it so that the ones and zeros that tell your CPU to open Google Chrome might be changed to an instruction to turn off your computer, for instance. So is 4.5 gigahertz the fastest clock speed we can achieve? Well, not quite. Consider the building block or the unit cell for a diamond. If there is an atom missing from this unit cell, it can act as a single photon emitter. These single photon emitters are the building blocks for quantum computing. They can solve problems that would take classical computers longer than the heat death of the universe to solve. So the main problem we are out to solve is identifying all single photon emitters in a given material. Now, how do we go along doing that? Well, we can just take the image of the material. Simple, right? Not quite. To get to the atomic resolution we are looking for, we use transmission electron microscopes, which shoots a bunch of electrons at a material you want to image. Then we have a lens at the bottom that collects all the waves, and we have an atomic scale image. But we run into a few problems. Consider the textbook image for hexagonal boron nitride, or HBN. Here, green are boron and gray are nitrogen. Now, this is an ideal image with no noise whatsoever. The atoms are perfectly still at 0 Kelvin, and we have a perfect lens with an infinite number of electrons being shot at the material. Even still, we have difficulties distinguishing from the borons and the nitrogens, but nothing a line profile can't solve. Now we have a great experimental image at room temperature. You can kind of see the atoms here, but it's very difficult. Now we have a realistic image on a bad day. We have incoherence because of the number of electrons being shot at the material aren't constant, and the lens aren't perfect. I have no idea where the atoms are. But wait, there's more. We have to do this for thousands of atoms in a given image. The material isn't uniform depth-wise, so we have some regions with more contrast than others. Some part of the image might move out in the next frame, while other parts of the image might move in the next frame. Over time, some random area might have defects created in it due to the intensity of the electron beams being shot to take the image of the material. And some areas with known defects might just get randomly patched up in a given frame. Because of all these random variables, line profiles will not be of much help. The solution is convolution neural networks. Consider an experimental image that we have taken. And now, for simplicity, we will divide it into 4 quadrants. It then uses special numbers called weights to assign each pixel in each quadrant an importance. The process of assigning single numbers to all pixels in this quadrant is called downsampling. So everything in this would be a 5, while everything in this would be a 4. It then tries to reconstruct an array of the original resolution, say 480p for instance, giving each pixel a level of activation. The higher the number, the greater the activation. These red blobs are highly activated areas which are either single photon emitters or other regions of interest. Based on how close we are to the actual answer, where all the regions with defects actually are, we changed the weights. But how do we know what the actual answer is, where all our special regions of interest are? We can do it in two ways. One is experimental, and the other is through simulation. The experimental method goes like this. You take an image, do a Fourier transform of it, filter out the noise in momentum space, do the inverse Fourier transform, where all the regions in red are non-perfect hexagons. Or we can use simulations. Using autoslice algorithms, we generated 1,000 training images with the areas of defects already known to us. And this is the result after training the neural network using experimental images. It finds all the defective regions automatically and categorizes them without any human input. All these classes are decided by the neural network. However, notice it is not perfect because we used only a single frame manipulated 1,000 different ways. A better result can be obtained using simulated images, but that is still a work in progress. In conclusion, HBN is great for quantum tech, neural nets are great for analyzing experimental data, and simulated images might make neural networks even more stronger. Thank you for your time.